So this one is assignment which is related to astrophysics. We have like first 14 questions we have discussed. Question 15. So in this question, stars are formed from gas clouds within galaxies. As the gas clouds contracts, an extremely dense core at a very high temperature is formed. Within the core, the hydrogen begins to fuse into helium. Why the core must be extremely dense and at a very high temperature for a sustainable fusion to take place or a fusion to take place. So, what is the reason? First, why high density is needed? So we have sufficient number of the collision between the particles, and why high temperature is they should be there, so it can overcome the electrostatic repulsion. So it can, because when temperature is high, then particles will move faster, so they have enough energy to overcome the electrostatic repulsion. So the purpose of having a high density, it will increase the number of collagen, and the purpose of having a high temperature, it will overcome the repulsion, electrostatic repulsion, and the nuclear can fuse. As a gas cloud contract, the internal energy of a system increases. Explain how energy conservation applies. So as it contracts, the internal energy of a system is increasing. So how this applies to the system during this period of a contraction? Like when it is contracting, the temperature is increasing, internal energy is increasing. But how this implies that the energy is conserved? So what actually happened? The total energy, the internal energy is what? Internal energy is a sum of like kinetic and in the kinetic and the potential energy of the particles. Okay. But what happened when it is contracting the it's not the what will happen? The gravitational potential. This is whenever height changes, the GP or gravitational potential energy is mgh. So if the height is decreasing, the gravitational potential energy will decrease. If a gravitational potential energy is decreasing, the internal energy, the sum of kinetic and potential energy of the particles will increase. So how this implies energy conservation? That the gravitational potential energy decrease for the whole system, and that is equals to increase in the internal energy. So when it collapses, the GPE, gravitational potential energy decrease due to height. And what will happen? The decrease in GPE equals to increase in kinetic energy or internal energy. How the fusion of a hydrogen into helium in the core enable a large amount of energy to be released. So what will happen? Whenever like nuclear fission or a fusion are happening, the mass is converted into energy. Both fission and fusion are exothermic. So when the mass converted into energy, there will be a mass defect, and you can work out the mass defect by using a formula E is equals to mc square. Like E is equals to mc square. If what will happen if there is a greater mass defect? If there is a greater mass defect is there, there in a greater amount of energy will be released. So how we write? So hydrogen is converting into helium. When hydrogen, even you can relate with the binding energy per nucleon. So when hydrogen is converting into helium, there is a mass defect. Like there's a change in the mass. And what happened to that change in mass is equals to mc square. So because of this change in mass, that has converted into energy or release energy. Each fusion is not releasing enormous amount of energy, but what will happen because the rate of a fusion is very high, as a like it happened in 1 second, number of fusion are more. As a result, enormous amount of energy will be released. So what actually happened? The mass has converted into energy, and we can work out how much energy is released by using E is equals to mc square. And the one fusion is releasing a small amount of energy, but because the rate is high, that's why it will give enormous amount. Then we have the Hertzsprung and Russell diagram, which shows the relation between the luminosity and the temperature. Remember, this scale is always a multiple. Like if this is this side, it will decrease, and this side it will increase. So it will be divided by 2 as we move on. So this will be 2500, this side multiplied by 2. So this will be 10,000 Kelvin. This also multiplied by 2, 20,000 Kelvin. So higher, start with a higher value and then start to decrease. Then luminosity and the temperature range of a different stars are given. On the Hertzsprung indicate on each star A, B, C located. So we have this, we have to use this diagram because on the Hertzsprung-Russell diagram indicate each of the star A, B, C, and D, and then we have to categorize their types as well. So when you check for A is having a low luminosity and a high temperature. So means somewhat A will be, because 0.001 someone A will be here. B is having also zero point 0.1 luminosity, like less than 1, and temperature is 400. So B will be somewhat here in this region. What about C? And B is a main sequence, so it should be like in this range, because this part is a main sequence star. Means the star, they have, if high temperature is high, they will have high luminosity. If temperature is low, they will have low luminosity. What about C? For C, temperature luminosity is 160. So it's like or and the temperature is 3. So it means luminosity is low, but the temperature is low, luminosity is high. So likely to be a red giant, as I already mentioned. And the last one, D, is there, which is having the same luminosity as C, but it has a very high temperature. So likely it will be a dwarf. So D will be somewhat here in this region. Because we have to label on the star. So this is they have the same luminosity, so they should be in the same line. And but the temperature is higher for D, so it is in this range. What type of star is A? This region A is likely to be a white dwarf, because white dwarfs have high temperature and low luminosity. D is likely to be a blue giant, or a main sequence also acceptable. But they did not ask us to table shown a luminosity, complete the table. Yeah. Okay, we have to complete the table. So A is a white dwarf, A will be a white dwarf because it has a low luminosity and a high temperature. Compared to temperature, the luminosity is very low. And this is likely to be a main sequence or a blue giant. Acceptable blue giant or main sequence, both are acceptable in this range. Then in part C, Polaris is a nearest visible star to the Earth and an example of a standard candle. State what astronomer mean by standard. When we say it's a standard candle, it means the star or a luminous object is having a known luminosity. Like standard candle means star with a known luminosity, like we know its luminosity. That is called a standard candle. Then recent measurement indicate Polaris may be significantly closer to Earth than the previous thought. Explain why this would have a significant impact on our estimation of age of the universe. So how it will affect the age of the universe, like in our calculation, if it is closer what we have calculated. So if the Polaris is closer, its luminosity will be less than what we thought, the known luminosity. And the distance of the other astronomical body would be less than what we have thought as well. Like, because like when we consider, we said it has a certain luminosity is there, but recent studies suggested that it is much closer to us than what we have thought. So if the Polaris is closer, its known luminosity will be less than what we have thought. And as a result, what will happen? If the idea is that the astronomical bodies that will have that would be less than what we have thought. So as a result, what will happen? The value of the Hubble constant will be greater. How the value of Hubble constant will be greater? We have the formula V is equals to H naught D. So V over D is equals to H naught. If the distance is decreasing, so the value of Hubble constant will increase. And what is the relation between the value of the Hubble constant and age of the universe? It is inverse. Like what reciprocal of the Hubble constant equals to age of universe. So the value of Hubble constant is greater, then the age of universe will be smaller. So the universe would not be that old what we have thought. Because, for example, if we are considering the objects, we are say this is us and we are observing object A and object B. The time taken by object A to move away from us is same as the time taken by object B. But they are moving with a different speed. So we have the formula V is equals to distance divided by time. So time is distance divided by speed. If a distance is longer, it is moving faster, but the ratio will be constant. Here, distance is shorter, it is moving slower, but the t will be constant. And this time taken by this object to move away from us is called age of the universe. So what they're saying if this object appear to be closer than what we have thought, like we thought A should be for like A was further when we did the calculation, but now the recent study shows that A is closer to us. So if A is closer to us, as a result, what will happen? Like if this was estimated age like 14.3 billion years, this if A is closer, then it means it is not 14.3, it will be less than 14.3. So how you can relate these things with each other? You can relate if like the star is closer to us, its luminosity would be less than what we have thought. And as a result, if the luminosity is less, so the distance will be like if a distance is shorter, the Hubble constant will have a higher value, and if a higher value of Hubble constant, then we'll have a shorter or a smaller age of the universe. Is it clear? This question 15 from astrophysics.